The Millau Viaduct is located over the River Tarn near Millau in southern France. The purpose of the bridge is to complete the missing link in the A75-A71 autoroute from Paris to Béziers and Montpellier and to reduce congestion to the Rhone Valley. This is particularly essential in the summer months during the peak tourist season. The Millau Viaduct successfully fulfills these purposes, and journeys have been reduced by over an hour, and congestion has been significantly reduced. The Millau Viaduct is a multi-cable stayed bridge with 6 equal central spans and 2 slightly shorter outer spans. These together form a total span of 2,460 metres. The structure was designed by British architect Norman Foster and French structural engineer Michael Verligo. The creative skills of both the architect and the engineer pushed the design boundaries to achieve the structure of immense strength that is gentle and elegant. Height is a characteristic that is highly emphasized in the aesthetics. The hexagonal cross-section contributes to the appearance of a slender structure in certain lighting. At certain times of the day, the low-lying cloud which surrounds the bridge gives the impression that the deck is floating. Since its opening in December 2004, the bridge has been consistently named one of the greatest engineering achievements of all time. The bridge cost approximately €400 million to construct. Before the construction of the Millau Viaduct, the Eiffel Tower was the tallest structure in France. This record was broken by the 343-metre tallest pier of the bridge. The Millau Viaduct is now the tallest bridge structure in the world and has the 12th highest bridge deck.
The 342-metre deck is supported by a single central span of 22 tension cables. These forces are transmitted down the steel pylons into the reinforced high-strength concrete piers before being transferred to the ground. The foundation design of the Millau Viaduct varies as there are 2 main soil types under the total span of the bridge. Both types of foundation adopted behave as a piled raft with the load being transferred to the footing. Marls, found under piers 6 and 7, is less resistant than limestone. The reinforced concrete piles in this weaker material are under-reamed and generally longer than the piles used in the limestone. The additional length provides additional skin friction, whilst the under-ream improves the bearing capacity. In marls, the footing is 5 metre thick compared to the 3.5 metre thick footing in limestone.
The foundation design of the Millau Viaduct successfully used Texagi's and Peck's observational method in an attempt to reduce the risks imposed from the uncertainties associated with foundation design. This method continuously monitors foundation behaviour during construction against the design model and selects the correct course of action predetermined at design stage when the real behaviour deviates from the theoretical model and exceeds the predefined thresholds for settlement and rotation identified at the design stage. The method has the potential to create time and cost savings as unnecessary contingencies are avoided. However, it requires high quality control and expensive equipment, and if used incorrectly, can be dangerous. As the cables are single span only, with live load supplied, they offer resistance to torsion in the deck. This resistance must therefore come from the deck itself, and hence a deep section is required. The incremental launching method adopted to construct the bridge requires a continuous cross-section, so the deck is relatively thick throughout its span.
To assess the torque acting, the following diagram have been identified at plausible load combinations. Only one lane has been considered, with no relieving effects on the other lane, as this is considered worst case. Case 1 is gives the highest moment out of all 3 cases. The deck profile looks like this and has been reduced to this in order to find the polar moment of inertia. The thicknesses are average values, red about. This is the equation to find the angle of twist. Torque is from the moments calculated earlier. J is the polar moment of inertia. G for steel is 77,000. And the length is taken between the 2 fixed points of 342 metres. This gives an angle of twist of 0.0322 degrees. This is the deck profile. The rotation of the deck is 0.0322 degrees. This gives a total deflection of 9 millimetres. metres. This is less than L over 800. This is the acceptable limit. So torque is okay in the deck.
The bridge is located in a valley, giving rise to funneling effects which increase the wind speed. The bridge is also susceptible to greater gust speeds due to its significant height. Extensive wind tunnel testing was therefore carried out during the design phase. The bridge is able to withstand wind gusts of 51 meters per second when operational and could withstand 90% of this value during construction. Heavy-duty windscreens are installed to protect traffic from side winds, as they reduce the effect of the wind by 50%, reflecting the speed of the wind found at ground level. Due to the wind effects, a system of rigid piers and pylons with a thinner deck was adopted as opposed to flexible piers and pylons with a thicker deck. The piers are also pre-stressed to prevent transverse wind loading from generating tension in the piers, which would cause cracking.
An incrementally launching system was adopted for the construction of the Millau Viaduct. Having constructed the foundations, the piers were erected in 4-meter sections simultaneously to allow for quicker installation of the deck. How is accuracy ensured?
Yup, yeah, you're good. Yeah, excellent. To the left a bit, flangy. Yep, alright, excellent. On time, 100%. Let's go.
GPS was used to ensure accuracy. To incrementally launch the steel deck, it was necessary to construct temporary piers at midpoints to reduce the bending moments in the deck. The prefabricated deck was transported in sections and assembled on site. When in position, it was then incrementally launched from either side of the valley. A single pylon and 6 out of 11 cables were adopted to limit deflections and moments in the deck. GPS was again utilized to ensure accuracy. The deck in place, the steel pylons were then installed and then the cables. Long bridge spans are subject to extreme horizontal movement as a result of changes in temperature. Under a frequent SLS effective temperature change of 24 degrees, the bridge has a 0.7 meter horizontal deflection. Under a rare SLS effective temperature difference of 40 degrees, the bridge has a 1.3 meter horizontal deflection. As the piers are fixed to the deck, these horizontal movements result in large stresses that can lead to cracking. Piers P1 and P7 are particularly susceptible to these effects due to the accumulated expansion in the deck. As a result, the piers are split into 2 shafts 90 meters from the top of the pier. 2 robot models of the bridge with split piers and single piers were analyzed to compare the differences in flexibility under temperature effects. The profile of the piers was simplified to 2 rectangular sections. A material property of concrete with C80-90 strength was applied to the sections. The red members in the robot model indicate the single pier profile and the blue split pier profile. The results showed that the split piers provided a reduction of deflections at the top of the pier by 50% and horizontal forces by approximately 70%.
This experiment will demonstrate the higher flexibility found in a split pier compared to a solid pier. A force P is applied horizontally at the top of the solid pier to represent the movement of the deck. The same experiment is conducted on an identical pier that was cleaved at the top. We can see that this pier is more flexible under the same load.